So this video is going to be in the playlist on vectors and matrices, and it's going to be a follow-on video from the video entitled The Definition of the Determinant of a Matrix. And in this video we're going to look at Laplace expansion for finding the determinant of a matrix. And we're going to understand why, one, it works to give the determinant of a matrix, and two, why all the different possible Laplace expansions give the same answer, and that answer is the determinant of the matrix. So that's what I want to try and get you to understand by the end of this video. So I'm going to begin by actually showing you Laplace expansion, and we'll do it in the case of a 3x3 matrix, and then I'll try and justify why it works. So if we take a general 3x3, here it is, A11, A12, A13, A21, A22, A23, A31, A32, A33. So in the previous video on the determinant, we saw how the definition of the determinant is you want to add together a bunch of products where the products are going to have one entry from each row and each column. So for example, this would be a product. A11, A22, A33 would be a product that would meet those criteria. Another one would be A12, A21, A33. That has one entry from every single row and every single column and only one entry. And you want to add all of those possible products, and there's going to be 6 in the case of a 3x3 matrix, together, except that it's a little bit more complicated than that. You don't just want to add them all together. Instead, you want to have a plus sign in front of some, and you want to have a negative sign in front of others. And that depends upon the parity of the permutation associated with that product. And if it's an even permutation, then it will have a +1 in front of it, and if it's an odd permutation, it will have a -1 in front of it. Now, before we go any further, I would just like to add a little bit more onto that. So let's take an example of one of these products. So this was an example we just stated. So those 3 things. So that's A12, A21, A33. So this is an odd product, because to get all of the indexes nicely in line with one another, you'd have to make one switch. You'd have to like swap this 2 with this 1, or you could swap this 1 with this 2. Now what I want to actually show you is that there's another way of thinking about these switches in terms of this picture here. So what you can really imagine we're trying to do is get all of these entries into this diagonal line. Now one of them is already in the diagonal line. That's brilliant. These 2 are the problem. They are not in the diagonal line. They're off diagonal entries. And the only moves you're allowed to make is to switch 2 things. So you're allowed to take 2 of your entries and switch their rows or their columns. So what we can imagine doing is taking this one and saying, let's switch which row they're in. Sorry, not which row, let's start with which column they're in. So if we switch which columns they're in, this one will move into this position. So the moves are only side to side or up and down, but you can grab 2 entries and you can say, I'm going to switch. They're going to swap columns effectively. They're not swapping positions, they're swapping columns. So swapping columns would move this one into here, and it would move this one into here, and you'd then have them all in a diagonal line. Equivalently, you could imagine swapping their rows instead. You could say, I'm going to give this one's row, and give this one's row. That would bring this one down here, and this one down here. This one up here. So that's a geometrical way of thinking about these, well, not a geometrical way, a pictorial way of thinking about what we're doing when we switch these things around. You can think about sliding these entries up and down, and what we're trying to do is get them into a diagonal line, and we're asking how many of these switches where you're moving 2 in parallel or in anti-parallel with one another, how many of these switches would you have to make in order to get them into a diagonal line? That's another pictorial way of thinking about this switching that determines whether it has a plus or a -1 in front of it. So it's really all about, when you have your product here, how badly is it not in a diagonal line? How off diagonal is this selection of things that you're producting together? And how many of these corrections, these switches, are you going to have to make to get them all sitting on a diagonal line? That's really what the parity of the product, whether it's an odd or an even product means, and whether it has a plus or a minus sign in the formula for the determinant. So that picture of the parity of a permutation is going to help us later when we justify Laplace expansion. But for now, let's go back to looking at what Laplace expansion even is in the case of a 3 by 3 matrix. So Laplace expansion is a method for finding the determinant of a matrix, and it can be applied not just to 3 by 3 but to indeed any size matrix. It would be a bit overkill to apply it to 2 by 2 matrices, and certainly for 1 by 1 matrices, but for all the ones bigger, so 4 by 4, 5 by 5, 6 by 6, n by n, it certainly applies, and it's a very useful tool. So let me show you how it works firstly, and then I'll justify it. So what you do is you can actually pick any row or any column to do your Laplace expansion around. And usually when we have a 3 by 3 matrix, we pick the first row. However, you could have picked the second row or the third row, or indeed one of the columns, the first column, the second column, or the third column. And in fact, if you've got a matrix where you have a column or a row that has a lot of entries that are 0, that would be a very good one to do Laplace expansion using, because the 0 is going to mean that you have to do much less computation, because all the entries with 0 are just going to vanish. But often, when beginners are first learning how to take the determinant of a 3 by 3 matrix, they use Laplace expansion with the first row, and this is what you do. So let's say we've chosen the first row. You start with the first entry in the first row, and you cancel out its row and its column. And you just look at this bit here, because what we're going to do is we're saying just think about the products that are going to involve A11. So of course you have to get rid of this row and this column. You can't have any more entries from the same row and the same column. And what you can do is you can write down A11 and then times the determinant of this smaller matrix, this reduced matrix, this little square 2 by 2 matrix here. So A22, A23, A32, A33. And when I do square, or not even square brackets, straight lines like this instead of curved lines, that means the determinant of this matrix rather than just times this matrix. Then you go to this second entry in the first row here, so that's A12, and this one's actually going to need a minus sign in front of it, and then you times that by its reduced matrix. You get rid of its row, its column, and then you look at this matrix consisting of these 4 entries, and you times it by the determinant of that reduced matrix. So A21, A31, A23, A33, and then you go on to the final entry of row 1, which is A13, and this one's going to have a plus sign again in front of it. So this one, you get rid of its row and its column, and then you times it by the determinant of its reduced matrix, which is A21, A22, A31, A32. And the big claim of Laplace expansion is that this thing overall gives the determinant of the huge 3 by 3 matrix. So if we expand this further, if we now work out what the determinants of these 2 by 2 matrices are, this is going to become A11 times, and then we're going to have A22 times A33 minus A32 times A23 minus A12 times A21 times A33 minus A31 times A23 plus A13 times A21 A32 minus A31 A22. So that's just filling in what these determinants of these 2 by 2 matrices are. So everyone knows the formula for the determinant of a 2 by 2 matrix. It's this one times this one minus this one times this one. And the claim is that that is going to give the determinant of the 3 by 3 matrix. So if you multiply all of this out, you're going to end up with a bunch of products of 3 entries with pluses and minuses in front of them. So let's think about why that works. So what you've done is, starting with this entry, you've said, let's get all the products which involve this entry. Now, you can't have anything in this row or this column, so exclude them. And then why does multiplying by the determinant of this smaller 2 by 2 matrix now work? Well, because what is the determinant of this? It's all the products of this matrix, all the products of two things from this matrix, where you have one thing in each of the rows and each of the columns. But can you see that when you multiply that now by A11, those products involving just two things here, they become products involving three things. And because of the way the determinant of this reduced matrix was defined, it's going to mean that you have one entry from each row and each column. And then because you've got this one, that then extends it. So you've now got an entry from the final row and the final column. So all of these products that you get through this are going to satisfy the criterion of being products of three things here, where you have one thing in each row and one thing in each column. Now, the more complicated bit is then understanding how it's going to get the signs correct. Well, in this case, it's not so difficult to understand how it's going to get the signs correct, because we have this reduced matrix here. We're taking its determinant. The signs that it's going to put in front of these products of two things are going to be whether it requires an odd or an even number of switches to get them into the diagonal lines. So it's going to have a sign that is appropriate for how many switches you'd have to make to get them into a diagonal line. Now, this one is already on the diagonal line, so you won't have to make any further switches when you add it into those products to make a product of three things. So the signs here, this plus here and this minus here, are absolutely fine being carried over to our formula for the determinant of the 3 by 3 matrix, i.e. this one can still have a plus and this one can still have a minus. The logic for this second one follows much the same, although it is slightly more complicated because we now need to understand why there's going to be a minus here. So, again, we're trying to find products now that involve this entry, A12, and so we can immediately exclude that row and that column because we don't want anything more from that row and that column. So we're just then interested in this matrix of 4 entries here. And if we took the determinant of that reduced matrix, it would find all possible products of two things where you just have one entry from each row and each column, which is exactly what we want to product with this to make products of three things that contain entries from one row and one column in the larger 3 by 3 matrix. So that, I hope you're starting to get why the determinants of these reduced matrices are so useful to us. It's kind of like an inductive process. From the determinants of these smaller matrices, we are getting the determinant of the larger matrix. In fact, it's not like that, it is that. That's what Laplace expansion is all about, reducing the problem of finding the determinant of this bigger matrix to finding the determinants of matrices that are one row and one column smaller. So in this case, 3 by 3 is reduced to 2 by 2. So finding this determinant of this 2 by 2 matrix gives us these two products, and the signs that it's putting in front of them, the +1 and the -1 here, are the signs that would be needed to get these into the diagonal line as far as this matrix is concerned. So this one has got a plus in front of it, this one has got a minus in front of it, because it would require one switch to get them into that diagonal line position. Now, remember where they are now in the larger matrix. They are not just a 2 by 2 matrix, they're here in the larger matrix. So being diagonal means being there and there as far as the larger matrix is concerned. Now, of course, it's more complicated than this first case because this first one was already in the diagonal, so we didn't have to make any further switches in going from these products of two things to the products of three things to get them all, make sure they're all in line in the diagonal in the 3 by 3 actual case that we're interested in, rather than just the 2 by 2 case. But here, of course, it's not the case. This thing is off diagonal, so we're going to have to make further switches from the switches that have already been made to make the determinant of the 2 by 2 matrix. And how many switches are we going to have to make? Well, it's only going to have to be one. We're going to have to switch whatever is in this position after this is done, with whatever is in this position, and that will then get them into the final diagonal position. But that means we've got to add 1 onto the necessary switches, the switches that were necessary to get them in diagonal line here. We have to add 1 to that to get them in the diagonal line here. So that means that the things that were even as far as the 2 by 2 matrix is concerned are now going to become odd, and the things that were odd as far as this is concerned are going to become even. And this is the brilliant thing about +1s and -1s, because multiplication does this all for us. If we just put a minus sign there, that's going to make this one that was even odd now, because we're multiplying through my minus, so it will become a minus overall product as 3 things. And this one, which was a odd product as far as the 2 by 2 is concerned, by multiplying it by minus, minus times minus makes plus, so it's now back to being even, which is exactly what we want it to do. So multiplication of +1 and -1 captures the same pattern as adding odd and even numbers together, and that's why it's so beautiful. So that's why there needs to be a minus there, because we're having to perform one final switch to get them in the correct diagonal positions that we weren't having to do for just the 2 by 2 case. Now, let's move on to the final one here. So it's the same logic. So we want all products involving this, so we can exclude this row, this column, and then if we take the determinant of this reduced matrix, this will give us all products of 2 things from there, such that you've got 1 thing in each row and each column, which is exactly what we need to multiply with this to give us products of 3 things, where you've got 1 entry from each row and each column for the 3 by 3 matrix. Excellent, so we're going to have plus A11 times the determinant of this. Then all we need to do is worry about the signs that we're going to get, and I note that that bracket has come out here. So again, the signs that we've got here are the signs that are created by getting things in the diagonal line for the 2 by 2 case, but let's think about what that actually means. Those are the signs of how many switches you would have to perform to get things in line like this in this minor matrix. So in this reduced matrix, it's going to get things here and here, which is no good at all. We've got this up here, and then we've got 2 things like that. How many switches are we now going to have to do to make this correct? Well, we're going to have to rotate things round. So we're going to have to bring this one up to here and switch this one down to here. And then we're going to have to do another switch. We're going to have to bring this one up to here and then bring that one down to there. So actually we need to perform 2 further switches to get the work that this has done in getting them into those diagonal positions into the actual diagonal positions that we want. And it's really crucial that you think about performing a rotation, not doing some bizarre switches where you switch this one and this one. It's very important to think about rotating it, because if we rotate it, we can maintain the relative positions of these. This is important when we generalize to higher, bigger matrices, and understanding why this works in the case of bigger matrices. We are going to try and maintain, these things are already nicely in diagonal in this smaller matrix. We just need to rotate them into the position so that they're in the final diagonal of the matrix that we actually care about. And to do that, we're going to gradually rotate this one into position, and in this case it needs to be rotated down to here. So we're going to firstly switch it with this one, bringing this one up here, and then we're going to switch this one up here. So it's kind of like rotating these 2 up here and then bringing that one down there. We're making that rotation permutation out of switches. And because it's, in this case, a free cycle, the overall rotation, it's therefore an even permutation. It's built out of 2 switches, 2 transpositions, and therefore it actually isn't going to change the signs. So you're going to have to add on 2 switches on here, but of course any even permutation here, when you add on 2, is still going to be even, and any odd permutation when you add on 2 is still going to be odd. So you can put a +1 there. You don't want to change these signs. These signs are absolutely fine. So I hope that has convinced you of why this method works. Now, before we go on to the higher case where we talk about n by n, I want to explain to you that Laplace expansion works for whatever row you pick. We could have picked a different row, or indeed we could have picked one of the columns to do this on. The same principle holds true. And to show you this, I'm going to take an example of let's do the second column. So I've picked something totally separate now, but I could have picked any of them. And I hope that doing it just for one, this very different second column now, will illustrate how this exact same principle is going to hold true no matter which row or which column you pick, that you're going to end up with the determinant here. So Laplace expansion using that column, we do exactly the same things. We go through each of the entries in the column. So we can start with this one here. We say, well, we don't want anything from that row, we don't want anything from that column, but we do want the entries in this reduced matrix, so these entries and these entries. So if we take the determinant of that 2 by 2 matrix, that will get us all possible products involving one thing from each row and each column. So the determinant of A21, A23, A31, A33, like so. And we are actually going to need a minus sign in front of that because it's in this position. So I'll tell you now how you work out whether you need a plus or a minus sign in these positions. So what you do is you do minus 1 to the power of I plus j. So for this one, I and j are 1 and 1, so you do minus 1 to the power of 1 plus 1, which is 2. Minus 1 squared is 1, so you want a plus sign in front of that. For this one, you've got I and j are 1 and 2, so it's 3 here, so you've got minus 1 to the power of 3, that makes minus 1. For here, you've got 1 and 3, that makes 4, that makes minus 1 to the power of 4, which is 1 again. So in this case, we've got 1 and 2 here, so 1 plus 2 is going to give us 3, minus 1 to the 3. We need a minus sign in front of there. Why is this the case? Because this actually captures how far away it is from the diagonal. So remember, what sign we want to put in front of here is all about, do we need to correct this, and do we need to correct it by an odd number of permutations, an odd number of switches, or an even number of switches? And whether we need to correct it by an odd or an even number of switches depends how far away it is from the diagonal here. So this one is just one maneuver away from the diagonal. You could move it into the diagonal either by going down one or by going to the side one. Both of those would bring it into the diagonal, so it's just one away from the diagonal. So it needs one switch to get it into the diagonal, so it will have a minus 1. This one up here, for example, this was 2 maneuvers away from the diagonal. You could move it down and then to the side, that's 2. You could move it to the side and then down 1. You could move it 2 to the side or 2 down. Those would all bring it into the diagonal, but every single time you have to make 2 little maneuvers. So that corresponds to needing 2 switches overall to correct things, hence why it had a plus sign. It wasn't going to change the order. And the reason that it's these numbers of switches is, again, because what we want to do is imagine rotating. So we don't make one big switch. We didn't suddenly say, okay, I want to switch this with this one down here. We wanted to maintain the relative order of these. So what we wanted to do is switch it one by one, move it down one by one. So we wanted to switch it firstly with this one, bringing this one up here, this one down here. So that was one maneuver. And then we wanted to switch it with this one here, bringing this one up and then bringing that one down a further one. So we wanted to make switches that only moved it one at a time. So this is effectively counting the number of switches that was necessary to perform that rotation to get things into the diagonal for the overall matrix. And don't worry, I will talk about this more. When we go to the n by n case, I will try and justify this, but I hope you're beginning to understand how this captures that number. So you can see that for any diagonal entry, any one of these, I and j are going to be the same, and therefore you're going to have an even number here, so you're going to have plus 1. For any off-diagonal entry, however many maneuvers it's away, so if you look at this one that's just one maneuver away, you have raised the j index here by 1, which therefore has made it odd. If you then make another maneuver away, you've either reduced or increased one of these by 1. Every single one of these maneuvers just changes these index by plus or minus 1. So each maneuver is switching it between being plus this minus 1 to the I plus j, is switching it from being plus 1 to minus 1. And that's why it captures this concept of how many maneuvers have you had to make to bring it into the diagonal. Maneuvers where I mean just moving it either to one side by 1 or moving it up by 1. So that's why this one will be even, this one will be even, these 4 will be odd, and all the diagonal ones will be even. And you can imagine how this pattern will generalize for bigger cases. So if you imagine having a 4 by 4 matrix, and I won't actually write the entries, I'll just put dots here for all the separate entries, then again the things in the diagonal are all going to be given +1 by this calculation, so they're all going to be red. The things immediately to the sides of the diagonals, these ones in blue, they are just one maneuver. You can either go to the side or go down or go up in some cases, but it's just one maneuver away from the diagonal. So that involves either reducing I or increasing I by 1, or reducing j or increasing j by 1. Just one change to this, however. So they're all going to be given the odd number, the -1 by this. Then going further away, the next line here, these ones, these are 2 maneuvers away from the diagonal. So you'll have had to change I and j twice, either raising them or subtracting them off. So that will therefore give an even number, and that's capturing the fact that it's 2 maneuvers away. And then finally, those ones in the corner, they're 3 maneuvers away, and therefore you'll have changed I and j 3 times by adding 1 or subtracting 1, and you'll therefore overall be given an odd number here. So that's why it's capturing this concept of maneuvers, and that number of maneuvers is then capturing how many switches would you have to make to perform the rotation that is going to correct the signs that we need from the lower determinants to the actual determinant that we're interested in. Gosh, okay, so let's carry on with our explanation here. So that's why this, I know that this has to have a minus sign here. And let's carry on. So then it's going to be A22. A22 is going to have a plus in it, because we're not going to have to change the sign of the products from the 2 by 2 matrix determinant at all, because A22 is perfectly in diagonal. So again, we'd exclude its row, its column, and we'd look at this reduced matrix, the 4 entries that are left. So that's going to be A11, A13, A31, A33. And if we take the determinant of that, it will find all products of 2 things that contain 1 entry from each row and each column, and that's exactly the products that we need to multiply with this to get us products that are going to appear in the final determinant of the 3 by 3 matrix. And then finally we'll have A32, and A32 will need a minus in front of it, again because it's just one maneuver from being in diagonal. Either it could go up or it could go down, so it's going to need to change the sign of all of these products. And again, we'd exclude its row, its column, and just look at this reduced matrix of these 4 entries, and we want the determinant of that reduced matrix, A11, A13, A21, A23. And if you perform this calculation, you're going to again get all of the 6 products that are needed in this determinant, and they're going to have the correct signs in front of them. So this is going to give also the determinant of this 3 by 3 matrix, and you can do this for any of the columns, any of the 3 columns, or any of the 3 rows. The exact same logic holds true for why this works. So this is called Laplace expansion, where you pick a row or a column to expand around. You have to put the correct coefficients in front of them, like so, according to this formula, and then you take each of your entries from the column and you multiply them by the determinant of the reduced matrix, which is the entries that you need to consider products of to make the products involving this entry of the column that are going to be involved in the determinant. So I hope that you can see that all of these different possible ways of doing Laplace expansion for this matrix are indeed going to give you all of the necessary products that you need in the formula for the determinant of this 3 by 3 matrix. The bit that still might seem quite incredible to you, and which I want to discuss further, is how are we making sure that the minus signs and the plus signs are all coming out correct? So I've already explained that for this case. I would like to examine that again in this case so that I can show you how it's working or demonstrate to you how it's working. And then what I'll do is we'll look at how Laplace expansion generalizes to the higher case and or the bigger case, 4 by 4, 5 by 5, n by n, and hopefully it will click into place for you. So looking at this one then, so we've got A12 here multiplied by the determinant of this reduced matrix. Now this determinant is going to have the two necessary products that we need, and it's going to have them with an appropriate sign that gets them into diagonal position as far as this 2 by 2 matrix is concerned. Now in our bigger 3 by 3 matrix, that's no good at all because it's going to put them into this position and this position. That's diagonal now. That's diagonal in the 2 by 2 matrix, but of course it's not quite diagonal in the 3 by 3 matrix. So what we're going to have to do is get this one now into the diagonal position. And the way that I've said we're going to do this previously is we need to do it by not changing the orders that these are in with respect to one another. So we want to rotate this one in so that we're not rearranging the orders of these relative to one another. So for example, if I was to switch this with this, I'd bring this up here and this one down here. Now that's no use at all as far as bringing them into diagonal. That's a counter-productive measure. But to illustrate how awful a move that would be, it's not only screwed up my ambitions of getting things into diagonal, but it's also changed the relative positions of these two with respect to one another. So I now might have to perform further switches of these two elements, which is not a good idea. I want to just rotate this one in without changing the relative positions of these ones so that I don't need to perform any more switches involving the ones in the reduced matrix, because we've already counted how many switches are necessary in the reduced matrix. This one has taken care of that. So I just want to rotate this one in. So enough talking, let me demonstrate what's happening here. So what we do is we only need to make one switch in this case. We switch this one with the one that's now in this position, that's been brought into this position by the switches that have already been made to find within the determinant of the 2 by 2. So that means we just need to make one final switch, and if you do that, that one will be in this position and that one will then be in this position. Alternatively, you could have imagined switching their columns, so bringing this one into this one and bring this one into this one. That would have also brought them into diagonal positions. And the point is that one further switch is necessary in order to get them actually in the diagonal positions for the 3 by 3 matrix. Therefore, you're going to have to turn the products that were even here into odd, and the products that were odd here into even, and multiplying by -1 does that. It turns the +1 into -1 and the -1 into +1. That's the brilliance of capturing, adding odd and even numbers with multiplying plus and minus ones. It's the same pattern, you know, if you drew out the 2 by 2 table of the different possibilities, they're isomorphic to one another. They're capturing the same pattern, the multiplication of plus and minus 1 and the addition of odd and even numbers. So then let's come on to this one here. So A22 is already in brilliant position. Then we've got our reduced matrix. This is then capturing, or this is then putting the correct sign in front of these products of two things to get them in the diagonal positions. So for A11, A33, that'll be a plus because it doesn't need any switches. For this one, it'll be a minus because it requires that one switch, switching this one with this one to bring this one up to here and this one down to here. So we don't need to make any changes to that because we don't need to perform any further switches, which is why this one has a plus sign there. So it's not changing the signs here because it's not adding any further switches in. This one then finally here, and I think, no, this is fine. So A32 is here. We've got the 2 by 2 reduced matrix here. Again, this has got the correct signs for bringing them into diagonal positions as far as the 2 by 2 matrix is concerned. Unfortunately, in the 3 by 3 matrix, diagonal positions are now here and here, which is not quite in diagonal here. So again, we need to perform one final switch, which is to switch this one with the one that's in here, bringing that down to here and that up to here, and that gets them into diagonal positions. So we need to perform one additional switch, therefore it changes the sign from odd to odd goes to even, even goes to odd, therefore we need a minus sign in front of there. So that hopefully convinces you that this is going to work as long as you put the correct signs here, and this is how you can work out the signs that you're going to need. It's how many of these switches are you going to need to perform where the switches are just neighbouring switches, so that they're making up a rotation, so that they're not overall changing the relative positions. And that is best illustrated with this one up here, where before, over here, we had this matrix, this 2 by 2 matrix here. It had got them into these two diagonal positions, and then we had this one, and we did not want to go into switching this one with this one, for example. It would have been an awful idea because we would have changed their relative positions. We want to keep them in the same relative position, so we want to do one switch at a time. We want to just switch it with the neighbouring one to bring this one up to here, so that it's still above this one. You know, you bring this one down here, but then if you look at the 2 by 2 matrix, so if you imagine now having brought this into this entry, you'd have this row crossed off and this column crossed off, and you'd now have these being your minor matrix. This will be here and this will be here, so they're still in the same relative position, still in diagonal as far as the 2 by 2 matrix is concerned. That's crucially what we're doing here. We're rotating it in without changing the relative positions of the ones that have already been fixed up by the determinant of the smaller matrix. And then once you've done that, you then switch it with the next one to bring that one up. And again, you haven't changed their relative positions. So that's why this is important. It's capturing how many switches do you need to do that very careful rotation to get the final one into position. And this is the correct formula. So it's how you determine whether you need a plus or a minus there. So what I want to do now is demonstrate to you how this generalizes to the n by n case. However, I think rather than actually try and show it to you for a general abstract n by n matrix, which I think is going to be quite difficult to demonstrate in a decent way, because, you know, writing out an n by n matrix is quite difficult. You have to leave loads of entries blank. You just have to put ... there. Instead, what I'm going to do is I'm going to do it for a 4 by 4 case, and you'll see hopefully how the pattern generalizes, and you'll get the idea, and you'll see how it could generalize to 5 by 5, 6 by 6, indeed, n by n. I think that's a better way of doing it. So bear with me whilst I write out a 4 by 4 matrix here. So we've got A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, and A44. Good. So we're going to find the determinant of this through Laplace expansion. So again, the same thing holds true. You could perform Laplace expansion around any of these rows or any of these columns. So the best option, if you're actually trying to compute this for a given matrix, is to pick a row or a column with loads of zeros in, because then the things at the front of the determinants are going to be 0, and therefore that entire term is going to vanish away. In our abstract case, we don't know that any of them are 0, so we don't have a better row to pick. So I'm going to pick just one that you wouldn't expect me to pick to show you. So we'll take this column here, column 4, and we'll do Laplace expansion using column 4. So again, the exact same thing holds true. So you can do it in whatever order you like, but we'll start logically, just methodically, with the top one. So we'll have A14, and now again we want all of the products, so we're not going to include anything else from row 1 or column 4, so we're then going to want all of the things for this smaller matrix, which is now a 3 by 3 matrix. So in the 3 by 3 case, our reduced matrices were 2 by 2 cases. In the 4 by 4, they're going to be 3 by 3. In the n by n, it's going to be n minus 1 by n minus 1. So this is going to be A14 times the determinant then of that 3 by 3 matrix, A21, A22, A23, A31, A32, A33, A41, A42, A43. And you could find the determinant of that 3 by 3 matrix again with Laplace expansion, as we've just shown for a 3 by 3 matrix. Now, we need to think about what the sign is going to be in front of this, and we're going to use our formula minus 1 to the I plus j, so it's minus 1 to the power of 5, so it'll be a minus 1 there. Next, we'll go on to A24, the next one down. So again, we exclude this row, this column, because we don't want anything from those rows and that column to appear further in the product. So what we now want is the determinant of the remaining reduced 3 by 3 matrix, which will then find all possible products of 3 things that contain something from every row and every column and just one thing from each row and each column, which is exactly what we need to multiply by A24 to get all the possible products of 4 things that involve A24 that are going to be included in the determinant of this 4 by 4 matrix. So it's going to be A24, and this is going to have a plus in front of it because it's minus 1 to the power of 6, times the determinant of A11, A12, A13, A31, A32, A33, A41, A42, A43, like so, and we continue on, so I'll complete it, but you'll get the idea. So it's then going to be minus A34, so this is going to have a minus coefficient because it's minus 1 to the power of 7. And again, we exclude that thing's row and that thing's column, and therefore we're going to want this reduced matrix. So it's going to be the determinant of A11, A12, A13, A21, A22, A23, A41, A42, A43. Brilliant, which will give us all products of 3 things, where you've got one thing from each row and each column, which is then being producted with this, which will give us all products of 4 things, where you've got one thing from each row and each column involving A34. And then finally, we'll then have plus A44 times the determinant of the 3 by 3 matrix A11, A12, A13, A21, A22, A23, A31, A32, A33. So I hope you understand why this is going to give us all possible products that we need to include in the determinant for this 4 by 4 matrix. It's because we're going through each one of these entries from column 4, and then we're multiplying it by the thing that will give us all products of 3 things that need to be multiplied by each one of these entries to make the products of 4 things that involve each of them. The only thing we need to worry about is, are the minuses and pluses going to be correct? So let's look at this one firstly, this one here. So this great big product here is going to have the correct signs in front of the products of 3 things that will get them in diagonal, or will get them in diagonal for the 3 by 3 matrix. But now in the context of the 4 by 4 matrix, that diagonal is here, i.e. it's just underneath where we need it to be. Now this is the reason I wanted to do this higher example, so you really understand what I mean by rotation. We do not want to go in and start, for instance, swapping this one with this. You might think, I want to get this one now down here, so let's just swap it with this one. But that's not a good move, because that then brings that up here. This one goes down here, so yeah, you've got that into position, but it was a really bad move because now you've completely destroyed the relative positions of these ones. You don't want to have to think about doing switches of these elements that this has already put into position. You just want to think about moving this one. And if we carefully rotate it, then we can keep these things in the same relative position, and we can work out how many switches it would take to get this into the correct position. So what we'd imagine doing is firstly switching it with this one, the one that's in this position, which will bring that up to here and then this down to here. We'd then switch this one with this one to bring that one up to here, this one down to here, and then finally we'd switch this one with this one, bringing that one to there and that one to there. So really we've rotated all of these upwards and this one down, and that's a 4 cycle, so it's made up of 3 switches. So it was necessary to have an odd number of switches to correct everything, hence why we need to have a minus there to change all of the ones that were even here to odd, and all of the ones that were odd here to even. And that's why the minus 1 to the I plus j captures this again perfectly, as I've tried to previously explain, because that captures how many of these maneuvers where you're just moving it either down or to the side once, how many of those are necessary to get it into the diagonal position. And because we're doing this rotation, we're making the switches are making up a rotation. The switches are just these one at a time little switches, not big jumps. We're switching neighboring things. That means that we are moving this just one at a time. It's being moved, it's switching with the thing that was in that row underneath it first, then it's switching with the thing that was in the next row down. So it is making maneuvers that are of this form, and therefore by counting just how many of those are necessary, we're getting the correct sign here. I hope that is clear. It is quite a complicated thing to explain. So let's continue on. So let's look at it again for another example. So this one here. So again, the signs that this will give the products of 3 things are the signs for how many switches it would take to get them in diagonal position for the 3 by 3. But diagonal position for that is here, here, and here, i.e. not quite diagonal positions in the larger matrix. So again, what we want to do is do rotation, do carefully picked gradual little switches, so which don't affect the relative positions of these. So we want to firstly switch this one with this one, bringing this up to here. Then we want to switch this one with this one, bringing this into here, and that will bring everything into diagonal. And again, you can see it's just counting how many of these maneuvers where you're only allowed to move downwards or side to side once does it take to get it into the diagonal position. So this formula is giving you the correct number of additional switches that you need in order to overall get things into the diagonal position for the 4 by 4 matrix. And you'll note how I've talked about how it could be switches from side to side or up and down, but I've always talked about doing it up and down. But you could have equivalently, you could have switched this one with this one first to get this into this position, this one into this position, and then switched this one with this one to get this into this position and this one overall into this position. So you could have done it side to side rather than up and down. I've just looked at up and down here because it seemed more intuitive, but they'll give the same answer overall. And we know, of course, that parity is all well defined. All of these switches that we're making, we could write them in terms of group theory notation. It has an analog in group theory capturing the same pattern, and we know that the theory of parity is well defined. We prove that in a video on the playlist on group theory entitled Parity of Permutations. So whichever way you do it, whether you're thinking about switching in the vertical direction or in the horizontal direction, you're always going to get the same answer in terms of odd and even. So we can just take whichever one is simplest, and this is a simple way of imagining it, going down in this way and doing it carefully so that we're rotating things into the correct position. And it continues on for these two. These are the same thing. You know, this one here, here's the 3 by 3 matrix. Things will have the correct sign from here that bring them into the diagonal as far as it's concerned, which is here, here, and here. And then this is the correct sign to perform that final permutation, that final switch that brings this one up here and this one down here. And then finally for this one, A44 is actually in the correct position, so you don't need to change the signs at all. So this formula, I hope you understand, does give you the correct sign that you need in front here to correct the odd and even parities that's in front of each of the products. So I think we will end there. I hope that I have managed to convince you of what I wanted to convince you, which is that The Laplace expansions are all going to give the same answer, whichever way you do it, whichever row or column you use to base your Laplace expansion around, they're all going to give the same answer, which is the determinant of the matrix. It's hopefully very clear that this method will give all of the necessary products that you need. I hope I've also managed to explain to you how this method of putting the minuses and the pluses here is going to give us the correct overall signs in front of each of these products. This generalizes to the n by n case. If we have an n by n matrix, you can pick any one of the n rows and any one of the n columns to base it around. And then once you've got your column or row that you want to do it on, you just go through each of the entries in that, you find its reduced matrix, take the determinant of that reduced matrix, multiply it by the entry that produced that reduced matrix, and then put the correct sign in front of it according to this, where you just put -1 to the power of the I and j index of your entry, so in this case 1 and 4. And you work through all of the entries in your row or column that you've decided to expand around, and just add them together with the appropriate sign in front of them, and that will then give all the products that are needed for the determinant, and it will give the correct signs in front of each of those products. So we'll end there. Thank you for watching.